When we read a paragraph, we experience it as a straight line. One word follows another, building sentences that stack sequentially from beginning to end. But the moment you look beneath the surface grammar, that linear progression shatters into a three-dimensional web of dependencies. Consider two blocks of text are syntactically flawless. Only one actually means anything. Coherence is not defined by the presence of good grammar. It is defined by the strict absence of non sequiturs. In a truly coherent text, every single linguistic unit has a specific job. Each clause exists to fulfill an intended functional role relative to the clauses around it, creating an invisible architecture of logic. The framework designed to map this invisible geometry of discourse is called rhetorical structure theory, or RST. If we can mathematically model this architecture, natural language processing, or NLP, the branch of artificial intelligence focused on understanding human language, shifts from merely parsing syntax to actually decoding human intentionality. Look at the computational limits of the 1980s. Early researchers were tackling natural language generation, or NLG, the process of producing human-readable text from computer data. Their systems could output individual sentences, but failed entirely at generating multi-sentence texts that read naturally. To solve this, researchers William Mann, Christian Mathiasen, and Sandra Thompson began a massive project at the Information Sciences Institute. Their methodology was deliberately agnostic. Stripping away assumptions about morphology and syntax, they studied purely functional relationships between text blocks. They concluded that text coherence is achieved strictly through a hierarchical connected structure, linking every part via specific rhetorical relations. RST was not engineered as an abstract linguistic philosophy. It was built as a pragmatic, language-agnostic algorithm to force computers to plan coherent thought. To see how this algorithm builds a coherent structure, we will analyze a highly technical abstract from Scientific American regarding the perception of apparent motion. The first mechanical rule of RST analysis is strict segmentation. The analyst must divide the raw text into minimal units before attempting to map any relationships, preventing them from using circular logic to justify a preconceived structure. The standard base unit in RST is an independent clause, along with all of its dependencies. This diagram shows the raw text strings from our abstract parsed into 4 distinct base units. Unit 1 is the title. Units 2, 3, and 4 break down the sentences of the abstract into these isolated clausal chunks. Setting the boundary at the clause level solves a major granularity problem. If the units are too large, like an entire paragraph, they contain too many overlapping external relations to map cleanly. If they are too small, isolating single words inside a clause, the analysis loses its focus on communicative intent. By forcing the isolation of these agnostic base units first, the framework prevents the analyst from reverse engineering the data to fit a specific structural conclusion. Once the text is segmented, we encounter a paradox of textual organization. Not all information presented by an author carries equal weight in realizing their intention. RST formalizes this asymmetry using 2 classifications. The first is the nucleus. This is the essential core information that is central to the writer's primary purpose. The second is the satellite, which contains secondary, supporting information that contributes directly to the nucleus. You can verify this weighting using a simple deletion test. A text remains broadly comprehensible if you delete the satellites, but it becomes entirely incomprehensible if you remove the nuclei. Looking at this schematic, we can map this relationship. Unit 3 is the central nucleus, containing the core action, while the structural arrow points to it from the satellite in Unit 2, which merely sets up the scenario. There is an exception for parataxis, the coordination of structures of equal importance. RST accounts for this through multi-nuclear relations, such as a contrast or a list, where 2 spans carry strictly equal theoretical weight. The principle of nuclearity proves that discourse is not a flat chronological chain of facts. It is an asymmetrical, weighted system engineered specifically to direct human cognitive attention. How does an analyst rigorously define the specific connecting line between a nucleus and a satellite? Every rhetorical relation is defined by 4 strict fields: constraints on the nucleus, constraints on the satellite, constraints on their combination, and the intended effect achieved on the reader. A condition arc bridges Unit 2 to spans 3 and 4. Relations nest together. A means relation connects Unit 3 to 4. This introduces recursion. Schemas are applied recursively until, zooming out, a top-level preparation relation links the title to the entire abstract body. A completed RST tree analysis must obey 4 absolute constraints: completedness, connectedness, uniqueness, and adjacency. Every unit must be linked, with no overlap, forming a single contiguous block. The completed RST tree visually proves that every single clause in a coherent document is architecturally tethered to a singular overarching communicative effect. For years, a major assumption in NLP engineering was that if a structural relation exists between clauses, it must be flagged by explicit cue phrases like because, however, or therefore. But exhaustive corpus analyses reveal an empirical paradox. Over 50% of functional rhetorical relations in diverse texts are entirely unsignaled by any lexical markers. We map identical logical structures regardless of the surface-level syntax. Whether 2 spans are explicitly linked by the word because, or the word is completely deleted, the underlying causal relation locking into place remains exactly the same. We have to differentiate between explicit discourse signals, like intonation, posture shifts, or coordinating conjunctions, and the deeper implicit relational propositions. These are the assertions that readers automatically infer based simply on their genre expectations. This forces us to separate intentions from relations. While coherence relations realize intentions, they are not the same thing. Intentions can apply to a single isolated proposition, while RST relations strictly govern the structural connection between spans. Because coherence is cognitively implicit rather than lexically explicit, NLP models cannot rely purely on surface-level keyword scraping. They must be engineered to infer this hidden structural geometry. This brings us to the theoretical limits of the completed RST tree. Is a strict 2-dimensional hierarchy genuinely powerful enough to map all the chaotic variables of human discourse? Consider the phenomenon of parallelism, where multiple simultaneous rhetorical relations hold true between the exact same spans of text. This directly breaks the classical RST rule of unique analysis. To represent this complexity, theorists propose transforming the rigid top-down tree into a multidimensional graph data structure, one that easily maps cross-dependencies and single nodes receiving input from multiple parent nodes. Furthermore, the gradual, chaotic development of spoken dialogue often breaks the strict adjacency constraints required by classical RST. Yet, despite academic debates over the exact taxonomy of relations, whether there are 24, 30, or 70, its core descriptive adequacy remains the gold standard in the field. RST stripped away the illusion of linear text to reveal the architecture of human intent. Nearly 40 years later, it remains the essential algorithmic blueprint for teaching machines how to truly comprehend language.